Greetings, and thank you for joining us today to learn more about scaling MySQL and consolidation on SolidFire. My name is Chris Mers, and I'm a database systems architect here at SolidFire. I've been architecting and scaling MySQL systems for over 12 years, including databases as service offerings and web-scale replication topologies. Today we'll be starting out with a brief overview of technologies comprising this solution, then diving into various scaling challenges and the strategies when using a next-generation data storage architecture. We're going to be looking at new and more efficient ways to operate MySQL systems at scale and the various benefits that can be gained from storage layer consolidation, including instant backup and restore operations, as well as vastly accelerated database cloning and replication slave creation operations. So let's go ahead and just talk about MySQL for a second. I like to call it the center of the web. Explosive growth and rampant success have natural consequences. In the case of MySQL, one of the most common effects of that adoption success is sprawl and manageability challenges. MySQL's unique role in powering the web, as we know it today, originated in the commonly deployed LAMP stack, originally Linux, Apache, MySQL, and PHP, leading to its wide adoption and ubiquity as the de facto database of choice in web platforms. MySQL would turn 20 years old in 2015, leaving no doubt as to the maturity of the database. The original development company, MySQL AB, was sold to Sun Micro, and when Sun was acquired by Oracle, MySQL came under the Oracle family of brands. Regardless of the magnitude of any particular deployment, MySQL performance is a touch point for all administrators, whether they're in the top tier of the DevOps world or the weary solo maintainers of client websites. After fundamental query sanity, the highest impact to MySQL performance is proper alignment with I/O resources. And when consolidating many database systems onto a single architectural platform, it's critical that the underlying storage layer provide a dedicated and appropriately scaled performance for the needs of the individual database instances. On a legacy SAN architecture, this was a very difficult, cumbersome, and expensive thing to do. So some folks may have heard this, and frankly I hear it a lot in the storage space. Who uses MySQL at this kind of scale that we're talking about? A lot of people. We've got Wikipedia, LinkedIn, YouTube, Twitter, a little company called Facebook, and of course a storage company you may have heard of called SolidFire. We use it as the backbone of our automated testing framework that validates the entire SolidFire product continually for quality and performance. It's also a critical component of ActiveIQ, our cloud monitoring product. So let's talk about SolidFire for a second. What is SolidFire? SolidFire is the all-flash storage array built for the next generation data center. The scale-out design leverages concepts of shared nothing architectures, creating a self-healing, high-availability disk subsystem with no single point of failure. The future evolution of data storage is made manifest in SolidFire, all while supporting enterprise-class SAN management features and efficiencies that unlock architectural flexibility. In addition, the fully functional API allows for complete automation and integration of the storage layer into a wide variety of infrastructures such as OpenStack, CloudStack, VMware, and numerous custom platforms. So when we think about scaling MySQL, many different images come to mind. We got traditional vertical scaling by using bigger servers with more CPU, RAM, and disk. Horizontal read scaling using read slaves and complex replication topologies. Database as a service where dozens or hundreds or even thousands of instances exist, otherwise known as DBAS. Right point scaling using various bolt-on cluster technologies such as MySQL Cluster or Percona or Galera products. And then homegrown solutions that incorporate characteristics from all the above, custom sharding solutions and things like that. So, this brings its own set of challenges. Some of the challenges that kind of come to mind when you're dealing with this type of scaling, if you dealt with it before, and I certainly have. It's you've got data center sprawl. You've got dozens of 1U and 2U boxes racked and stacked to meet scaling needs. There's capacity planning. What capacity will the databases require in 1 month, 6 months, a year, or 3 years? What about throughput and IOPS? You've got architecture lock-in. You've carved out disk groups and LUNs, but requirements change. Now what? There's always storage provisioning lead time. How long does it take to get the proper LUN provisioned? Are you out of shelf space? Do you need a new controller? There's performance projection. As various applications gain adoption, the back-end database characteristics change. When to migrate to more powerful storage is a big question. Then there's unexpected application load. What happens when an app, a game, or a site goes viral? The database is the least fluid and flexible part of the architecture, and traditionally the storage is the least flexible part of the database server. There's replication instantiation time. Horizontal scaling of complex database queries is usually accomplished by adding read slaves, but the time it takes to create and sync those replicas is a bottleneck. A 1 terabyte database can take many hours to copy and restore, adding lag and operating expense to the scaling procedure. Then there's storage hotspots. Traditional shared storage systems have a common Achilles heel in storage hotspots. Physical disk head contention, controller bottlenecks, things like that can bring legacy SAN to its knees, killing performance and basically hamstringing the entire enterprise. It takes out not only the one database, but everything else on the array. So this requires a paradigm shift. So obviously, the next generation shared storage solution has got to offer this type of shift to address these challenges that we talked about. So flexible and agile capacity provisioning. Utilization efficiency is key, and SolidFire solves for storage efficiency like no other offering on the playing field. With SolidFire, you provision capacity and IOPS independently of each other. Our advanced data placement algorithms allow for flexible provisioning of disk volumes, the ability to grow a volume with an API call or by moving a slider bar, and the ability to create new volumes with their own performance and throughput guarantees on the fly. There's no lengthy LUN carving and configuration procedure. You just make a call to the API or a few clicks in the UI and you're on your way. You also are able to custom tailor IOPS for each MySQL instance or instance type. You can configure minimum, maximum, and burst IOPS settings for each and every volume. You can ensure that each MySQL instance has exactly what it needs. The minimum limits ensure that the application will always meet performance requirements. The max ensures that no one particular MySQL instance will impact the others on the system. You can guarantee quality of service for each and every MySQL volume. It's not a best effort or a queuing system. It's a metric-based system based on IOPS that honors specific designations, allowing you to engineer your database solution rather than the kind of plug-and-pray you get in a priority tiering scenario. QoS is set for every volume in the system, allowing for granular control over the architecture. So what this does is allows you to safely run mixed MySQL workloads. QoS allows you to run production, replication copies, QA, dev test, reporting, and other ancillary MySQL instances all in the same storage array. The guaranteed IOPS configuration, that min, max, and burst that we talked about, enables dedicated performance in a shared architecture. SolidFire does for storage basically what VMware has done for compute and memory. In addition to that, thin provisioning and zero block identification allows you to actually only use the physical space you need while allowing for greater logical provisioning. The SolidFire management features alert you to physical capacity utilization thresholds, allowing you to order more nodes as needed. And then you scale out to meet actual demand, not projected thick provision capacity that sits idle for quarter after quarter depreciating. Let's talk a little bit about data protection for MySQL and SolidFire. So we have something called double helix, and it's block level replication. It eliminates the need and the hassle of dealing with RAID. Every 4K block in the system has a partner block and a different drive and node, ensuring 100% availability and allowing for any component in the system to fail without any impact to production operations and I/O or any impact to I/O service to the MySQL database instances that are there. The way that double helix works also allows for incredibly fast drive rebuild times. Since the 4K data blocks are distributed across the entire system, across many nodes and many disks, if a disk in the system fails, all of a sudden the secondary block takes over, becomes primary, and the entire disk is rebuilt in different locations using available space in the array. Instead of several hours of exposure during a RAID failure, you get about 5 minutes or so, and then the drive is rebuilt. The data from that drive is rebuilt on other areas of the array. And that means that can happen in parallel. If for some reason an entire node were to be lost, takes about 17 minutes for a shelf of 10 disks to be completely replicated throughout the system, because everything is distributed dynamically across the entire array. So also, in terms of data protection, we offer with SolidFire some instant snapshots, which can be used for backup and restore. SolidFire volume snapshots create instant crash-consistent backups from MySQL, and those snapshots can be cloned as a means of creating database copies in mere seconds versus hours for traditional restores, even using advanced solutions like Percona's Extra Backup. And in addition to all of that, SolidFire offers array-based replication for DR purposes. If you have two SolidFire arrays in different locations, you can replicate volumes from one site to the other, ensuring that you have DR copies of data in compliance with various DR plans. So let's go ahead and take a closer look at the instant snapshot backup and restore. And we'll just do a quick demo here. I'm going to go ahead and share my screen and get started with that. So, going. Okay, so first off, we go into SolidFire UI and we take a snapshot of the volume that we want to take a backup of. We'll just use the default naming conventions, just a timestamp. We go in here and we'll take a look at what we've got in MySQL. So we've taken the snapshot. So now we're going to show the databases. We see that we've got a bunch of databases in there. For our purposes, we're going to use foo as a test database. We're going to show the tables. There's a table called bar in there. And the data inside a bar, just a few rows, looks like that. This entire data server, this MySQL instance, is about half a terabyte in size. And we're just going to restore the whole thing. And we'll just simulate a failure here. We're going to drop database foo. We've now dropped the database. We can see that it's no longer there. I suppose you could say we're foobarred. So we're going to go ahead and to restore this, we go stop MySQL, obviously. And then we're going to go ahead and unmount the file system. We don't have to unmap the iSCSI LUN or anything like that. So now we've unmounted the file system. We're going to roll back the volume to the snapshot. Simple click operation in the UI. That's it. Now we mount back up the file system, very simply. Once that's done, go ahead and start MySQL. It's going to go through checkpoint recovery, run back through the log real quick. Right there, success. Then we'll go ahead and take a look and see what we've got. We should see exactly what we had before. So show databases. And there we go. We see foo is back. Go ahead and use foo. Take a look at the bar table. And there's the data. Simple as that. That is for half a terabyte restore, that's pretty darn fast. So let's go back. That's just one short, quick demo of the features of the system in conjunction with MySQL. We're going to take another look at this in a little bit more depth later when we do a replication instantiation clone. So let's talk about data efficiency with MySQL and SolidFire. So SolidFire makes the most of Flash. With inline data block compression for every MySQL storage block, in addition to dynamic capacity and thin provisioning, SolidFire employs this inline compression, creating additional space efficiencies for every page and block of MySQL data. Another critical efficiency capability that SolidFire adds into the mix is cluster-wide deduplication. Dedupe happens at a very fine granularity, so that if any 4K data block matches any other in the system, only a metadata pointer is stored and no underlying physical capacity is taken up by the duplicate data block. This is completely transparent to the host servers and application clients from all aspects, including performance. They see everything as if it were thick provisioned and dedicated storage. Deduplication enables a huge efficiency lever in that the more copies of a database you have, the more efficient the storage becomes. So really, more is less. So also we have thin provisioning that allows you to plan ahead and provision logical capacity for MySQL, avoiding the need to adjust and grow file systems later on, or add disks to LVMs, hoping the striping works out properly. You just provision a terabyte or 4 terabytes or 8 terabytes and create the file system accordingly as you normally would. Since most of that is empty space, SolidFire is going to zero it out, and it's only going to use as much physical capacity as there is actual data on the volume. And then when you start adding these things together, you add the cloning feature plus the deduplication to make database copies. You truly get back to that more is less idea. Clones leverage the deduplication so that you can create read-only copies of MySQL with minimal physical space, really multiplying out the actual efficiencies you're going to get by an X factor. You make 2 copies, it'd be 2X, 3 copies, 3X, so on and so forth. And you can really, when you're using an environment that has highly leveraged copies of the database, you can really, really make efficient use of your storage that way. Okay. So let's talk about web scale for a second. When you're on SolidFire, you're going to be able to streamline deployment time and storage efficiency for web scale replication. When you combine the various next generation features of SolidFire scale-out storage with the speed of an all-flash architecture, you kind of have the ultimate storage layer for creating web scale replication topologies. If you need to create a dozen read slaves to service the back end for a viral mobile application, not only can you create the additional MySQL database copies in seconds, the cloned databases don't take up appreciable extra disk space because of deduplication. This snap, clone, dedupe strategy holds true for read slaves, copies of MySQL for reporting, QA, dev test, and any other use case where you need a separate copy of the database. To give you a realistic look at how straightforward this process is, let's run through another quick demo. So in this demo, we're going to show how to leverage SolidFire's enterprise storage capabilities to create a production-ready MySQL replication clone in a fraction of the time that's normally required. This example database is also over ½ terabyte in size, and it would usually take several hours to clone and make ready in a traditional environment. So first off, we'll need to get replication point in time to start from. If you've done this, it's basically as simple as flushing the tables and then going ahead and doing show master status. And that will go ahead and show us the bin log file and the position that we're going to need. We're going to save this for later because we'll need it when we start up replication. We go into the SolidFire UI, go ahead and create a snapshot. We'll name it something reasonable, like I don't know, replication snap in this case. And just like before, we created the snapshot fairly quickly. We go back in, we unlock the tables. So while the master database is cruising along servicing the application, we'll go back over to SolidFire and create a volume clone from the snapshot that we just took. We go ahead and find our desired snapshot under the Volume Snapshot tab, and then we click on the Clone from Snapshot, give it a descriptive name. We'll assign it to MySQL read 01 because it's going to be a read slave. We'll assign it to the account that's associated with the VM. And this will be a read slave. So and just for giggles, we'll create another one just in case we wanted to create read 02 later on. And we'll go ahead and log into the read slave host, which was created using a VM clone operation in VMware, and we'll attach the new iSCSI volume. So now you can see the IQM there, and so it says MySQL read 01. We'll go ahead and just attach that login to it, and then take a look at fdisk and show us that it's actually there. Dev SDB is now being presented to that VM. And that is the cloned data volume for MySQL. We'll go ahead and mount it and go in and take a look at it. There's only a couple changes we need to make at this point. We need to edit myCNF, change the server ID from 1 to 2, make sure we don't have any conflicts within replication. And then as of MySQL 5.6, we need to get rid of the auto.cnf file that's got a UUID that is generated as of MySQL 5.6. And so we'll go ahead and bounce MySQL, and when this comes up, we should basically have a clone that's ready for us to start replication on. So we'll go ahead and add the master information, change master host. give it the IP here. We'll go ahead and add the username, something like REPL, whatever you happen to use in your application system, and password. Let's see, this isn't actually the password, but you get the idea. And we'll go ahead and go back over and grab that binlog file that we saved from earlier, 09, and then we'll add that, and then we'll go ahead and add in the master log position, in this case 120, and that'll give us all the information we need to start replication from this cloned volume sync of a ½ terabyte database. So we start up replication and go ahead and show slave status, take a look at how things are going, and you see there's no errors reported. And if we go back up and take a look at slave IO running and slave SQL running, both are yes, which indicates that replication is running as expected and that we're 0 seconds behind master. So there we have the entire operation for creating a MySQL replication slave, which would normally take many, many hours to complete, given the backup and the restore times, and then how long that takes versus how many seconds behind master you're going to get, because after you do 3 hours of export and 3 hours of import, you're 6 hours behind master. That's going to take you another couple hours for it to catch up once it starts syncing. Because all of these operations are compression and shortened, the whole thing takes a lot less time. And this is all manual. If you scripted this process in whole or in part, it could be even faster. But then we'd have nothing to talk about during the demo, because it would just be too fast. So that's that's one of the most powerful things that we can do. And as an administrator and architect, to me, that's something that really jumps out as a game changer. Really cutting down on operations and time and just general headache. So we've seen a couple of things you can do with MySQL and SolidFire. Another thing that we do offer for customers who are running MySQL on SolidFire, we've developed a set of best practices, and this is basically goes in depth into various tunings, operating system tuning, things like the no-op IO scheduler, file system and mount options, things like no barrier, which is incredibly important for IO throughput performance. No barrier specifically is something where it basically says if you have a battery-backed cache on your storage subsystem, then don't bother checkpointing and doing a barrier write for every disk operation. It really increases throughput, sometimes 40% or more. There's specific things with InnoDB in MySQL and SolidFire, like max IO rate, which affects how the flushing behavior in MySQL works, and how much it's going to flush at any given time, and therefore basically the kind of interpreted interval at which that's going to run. Things like the optimal SolidFire setup, volume configuration, things like that. And then of course, utilizing SolidFire features with MySQL, things such as the snap clone demo that we ran through, the backup and restore operations, things like that. So more or less, to recap here, scaling MySQL efficiently, regardless of the particular use case, benefits from the fundamental paradigm shift that SolidFire has brought to the technological arena. In consolidating to SolidFire, no longer do you have to choose between over-provisioning and resource guarantees. Whether you're consolidating hundreds of MySQL instances, growing a single system to web scale, or deploying a MySQL DBaaS offering, true performance at scale demands constant low latency, guaranteed quality of service at the data volume level, as well as an enterprise class feature set that promotes storage efficiency and streamlines deployment and operations. So only the SolidFire all-flash array series provides true scale-out in a shared nothing architecture with metric-based QoS, providing the most versatile, flexible, and agile storage layer available on the market today.
If the next step forward in storage intrigues you and you're interested in the competitive advantage that SolidFire platform provides, get in touch with us today and schedule an in-depth session with our team of technology experts.